signed backbone extraction from intrinsically dense weighted networks. So Furkan, the floor is all yours. Please share your screen. Yes, you can go.
Welcome everyone, and thank you for joining my talk. I am going to present our work on obtaining sparse signed backbones underlying intrinsically dense weighted networks. This is a joint work with my supervisor Bertan Badur. In real-world networks, thanks in part due to the more sophisticated data collection techniques, growing size and variety of data, such as more nodes and links, and associated weights, directions, and signs can provide accessory information. However, link and weight abundance results in denser networks with noisy, insignificant, or otherwise redundant data. Moreover, many typical network analysis and visualization techniques presuppose sparsity and are not appropriate or scalable for dense and weighted networks. Therefore, only the relevant and significant information should be retained from such networks while preserving adequate structural information for efficient and effective analysis. This problem in the literature is known as network backbone extraction. More formally, the problem we tackle in our paper is as follows. Given an intrinsically dense, undirected or directed, and non-negative weighted network, extract a meaningful and statistically sound signed network backbone that is sparse and also optionally weighted. We use the term intrinsically dense for characterizing networks where all nodes, in a sense, are aware of all other nodes and can interact with them without obvious natural limits. For instance, in a party with 12 people lasting several hours, we can talk about a positive link when 2 people interact more than expected. And also we can talk about a negative link when 2 people interact much less than expected. Our null model assumes that every time a node increases its out strength by 1, that is, increasing the weight of one of its outgoing edges by 1, or creating a new outgoing edge with weight 1, it randomly chooses the other node with probabilities proportional to their in strengths. Such process can be modeled by hypergeometric distribution. On top of hypergeometric distribution, we employ iterative proportional fitting procedure to ensure that in strength and out strengths are preserved. And eventually, this model yields expected mean and variance values for any pair of nodes. We propose 2 filters to extract the backbone. Significance filter retains links whose weights are far from their expected values based on 2 hyperparameters, alpha minus and alpha plus. The significance filter might retain statistically significant but otherwise very weak links, yet NH can be evaluated also based on whether it is sufficiently strong in terms of intensity and not only in terms of whether it is statistically significant or not. Instead of the distance in significance filter, vigor filter looks at the ratio of observed and expected weights and retains only those who are sufficiently intense based on 2 hyperparameters, beta minus and beta plus. Using these 2 filters in combination, we can extract the underlying signed backbones. We conduct our empirical analysis on 4 real-world networks. Migration network reports interstate migration flows in terms of people among the US states in 2018. Eurovision network represents the votes between participant countries of the European Song Contest in 2003. That is the last year where all countries competed in a single round altogether. Contact network data is gathered via wearable sensors at an academic conference, measuring the interaction duration between participants of the conference. Species network is based on the cohabitation patterns of 62 marine species in South Florida, and it's a kind of similarity network. In selecting these data sets, we ensured variety in terms of source domains and also the structure of the networks. The link weights and node strengths usually have a multi-scale nature, as is the case with many real-world networks. Here, we see how number of nodes and edges change for different hyperparameter settings. Each of the three columns have a different Vigor filter. X-axis denotes the alpha values used for significance filter, and Y-axis denotes the retained percentage of all possible nodes and edges. We can observe that almost all nodes are preserved, retained, even when the backbone is quite small, except for the species network where still more than 70% of all nodes are preserved. Similarly, positive and negative links are in comparable numbers for meaningful sparse backbones. By meaningful sparse backbones, that is when the backbone is small, but no smaller than it should actually be. Here we have a similar figure, but this time columns have different significance filters instead of Vigor filter, and x-axis denotes the parameters veta for Vigor threshold. I will not go into its details much, but we can obtain similar results as in the previous figure. However, it should also be noted that the parameter values should be selected a bit carefully, especially if employing extreme values, since they might distort the structure of the obtained backbone. Now we'll look at the results of heterogeneity. Here we see the original weights of the retained edges. Each backbone is obtained with different hyperparameters and retained 25, 10, or 5% of all edges represented in y-axis. And x-axis shows the original weights of these edges. Even when only 5% of edges are retained, we can observe that the edge heterogeneity is respected and the backbone contains edges with originally with This is unlike very simple information filtering methods, for instance, where only edges satisfy. Here we see a similar figure showing two ends of the retained edge when the backbone size is 20%. We observe that backbone preserves the structure and large strength nodes, preserving the multi-scale nature of the original network. If our method is any good, then the backbones obtained by it should have the same or similar characteristics in most cases. Here, for directed backbones, we see that positive edges are usually reciprocated by positive edges. The same is true for negative edges. For migration network, reciprocal links with different signs. However, networks, we observe that structural balance phenomenon generally characterized by the phrase, friend of my friend is my friend.
Okay, I think we lost you now.
Can you hear me?
Yes, but the connection, I think your connection is not that good. I think we lost your presentation. Yes, we can see it now. Yes.
Has it been like that from the beginning?
No, from the beginning. I think that here where you.
It's just.
you are stuck just at this slide here, so I guess you can finish it. We lost you again. I don't know. I don't hear you anymore. The video is going on, but we don't. I think your internet connection is not that good. Can you maybe restart from those last 2 slides? Not from the very beginning, because we don't have time for that.
Finally, obtained backbones exhibit a community block structure appropriate for signed
What now?
Yeah,
when you share the video, it's quite slow, right?
Are within communities and negative.
Okay, let's finish it like that. So leave the video on, and we'll try to catch. Because I guess we cannot do otherwise.
Links are okay. I don't know if you can hear me now, but
yes, I can hear you. I think that the connection is
good. So we were already in the conclusion.
Yeah.
So basically,
okay.
Okay.
Yeah, maybe you can describe briefly the conclusion. Okay.
So in conclusion, so our methods can obtain sparse backbones while maintaining comparable numbers of positive and negative links and respecting the original weight and strength heterogeneity. And these obtained backbones exhibit characteristics typically associated with signed networks in real life, such as reciprocity, structural balance, and community structure. But the method depends on the use of method requires choosing appropriate hyperparameter values a bit carefully, and this is more like a problem-specific choice. So the preprint of these and all the references, citations to other papers that we look for and the data sets is available today on arXiv, and feel free to email me even after the meeting. So thank you for joining and to my conversation.
Okay, so thank you very much, and sorry for this inconvenience.
Absolutely.
It was very nice talk indeed. I mean, we got like 95% of it, but just at the end, it was cut a little bit short. Maybe you can put the link. Okay, you put the link there. Okay, perfect. So people can access it. Now, if from the audience there is any question, or you can put it on the chat and I can read it for you. Otherwise, feel free to turn on your microphone and your video and ask it yourself. So meanwhile, from the audience, they are still thinking about it. I had actually a couple of questions. So my first point, when I see this kind of works that are, I mean, widespread in terms of filtering metadata in order to recover network structure, not only, but the adjacency matrices, even from not simply qualitative, but even quantitative point of view. My question is, okay, you have a filter there. Why you choose certain parameters for the threshold, so where to cut the metadata, how to interpret the metadata beyond the simple formula that you have. I mean, if you choose the different parameters, I guess that you recover a different connection matrix, right? Is there a ground truth to compare it? For instance, you recover an adjacency matrix. Do you simulate a model and to observe exactly the same phenomena that is observed in that kind of complex systems that you are recovering, let's say, the interaction networks?
That's a good point. So actually the hyperparameter values, we see that it depends on the network and also the magnitude of the network weights and the problem at hand. So for instance, Vigor filter, the Vigor threshold, we have a physical meaning. That is, if it is twice the expected value, then we know that it will have a certain specific value. So And depending on your problem, on your domain, if you think this makes sense for you, if it's meaningful for your problem, you can have this choice. Second thing, when choosing parameter values, so I tried with many different parameter values. So as you make it less, more strict, then you obtain smaller and smaller backbones. So they are not always completely different, but just you retain fewer links or more links depending on how tolerant you are with your parameters. And the third thing, and I think so far as I understand from the data sets that I look, it needs a bit empirical analysis, because at some values you really obtain, retain most of the nodes, and you have comparable number of positive and negative links. So it shouldn't be too small or too high, the thresholds in general.
Okay. So thank you very much. Thank you again, the speaker. Let's move on now to the next talk. The next talk is from Geza Odor. So I'm not very good in pronouncing Hungarian names. I apologize for that. From the Center for Energy Research at Budapest University will be about synchronization dynamics of the Kuramoto model and the large human connectome. So please, the floor is yours. Share the screen and then go ahead.
Yes, thank you very much. I have a pre-recorded talk, so
please.
I hope let me see, in full screen. Do you see?
Yes, you have a green rectangle somewhere in the left, upper left.
Yes,
maybe is a Twitter window, sorry, the Zoom window.
I am not sure how to remove it, because this is the
player. Okay, is the frame of the player, I see. Well, it's not a big deal, right? So, but I mean...
sorry, I don't know how to remove it. Just I will play it like that, okay?
Okay, it's perfect, okay. Maybe you have... Oh, sorry, can you stop for a moment? Because I think you have some other windows there open, or it's just my feeling. So you should have also the Zoom window that we see that. Maybe you can close the Zoom window where you can see the other participants. So
which window you mean?
No, now it's okay. But when you play the registration, it appears that it's okay. Let's try again. Let's try again.
Good afternoon.
Okay.
My name is Geza Odor. I am from the Complex System Department of the Institute of Technical Physics and Material Science, Budapest. I shall present you some results in collaboration with Jeffrey Canning from Dresden and Gustavo Deco from EPF Barcelona. I shall begin with some introductory sentences. Theoretical research and experiments suggest that the brain operates at or near a critical state between sustained activity and an inactive phase, exhibiting optimal computational properties. This was shown first by Bex and Planks in 2003, where electrodes were displayed in the brain and probability density functions of activity avalanches were shown to exhibit power law tails. These experiments and others were repeated later, and nowadays the critical brain hypothesis, which is very commonly used. Another experimental fact is that individual neurons emit periodic signals. Now the question naturally arises if there is a critical behavior at the synchronization transition. To investigate this, we used the simplest oscillator model introduced by Kuramoto in 1975, which is a nonlinear ordinary differential equation for the phases. At I, interconnected by edges with integrals ki, and there is a global coupling k, and the nodes have a weighted connection described by the adjacency matrix Wij. Furthermore, each node has its own intrinsic frequency oscillator. The order parameter we investigate is the average phase. This is non-zero above the critical coupling strengths, K greater than Kc, equals to zero below Kc, and right at the critical point, if we start the system from an incoherent state, there is an initial power law growth characterized by the exponent eta. It is known that critical synchronization transition can happen only for a larger than 4 spatial dimension, which is mean field line. In lower dimensions, you can still see some crossovers, but the dynamical behavior suffers very strong correction to scaling and chaoticity, which we have been investigated recently on sparse random networks. We have implemented this Kuramoto equation on graph of large human connectors. These are generated by diffusion and structural MRI images with 1 millimeter cube voxel resolution. Therefore, there are a huge number of nodes. These are hierarchical modular graphs with the top level of the southern brain region coming from the Desikan atlas. The lower levels obtained by deterministic cartography by the so-called FACT algorithm. A mapping was done from voxels to vertices, fibers to edges, and after a noise reduction, you can get a graph which is undirected but weighted. So this is a structural graph of nodes containing about 10,000 neurons and power law wide distributed edges. We have investigated the topological behavior of these graphs and found some kind of universality among them. Therefore, we selected a representative graph, the so-called KKI18 graph, which has 800,000 nodes, 41 million weighted edges. First, we determine the synchronization transition point by a growth from the disordered state. As this graph has a topological dimension smaller than 4, there is a smooth crossover from incoherent to partial synchronized state, as it can be seen in this graph by varying the control parameter K. There is a critical coupling of this crossover point at 1.7, where the growth exponent can be deduced from these curves, or more precisely from the local slopes of them. So these curves are showing the time evolution of the order parameter as a function of time, and the z shows the effective exponent, and in the infinite time limit we can read off the eta. But to find critical behavior, we have to apply a weight renormalization. This is due to the fact that the weight has this power law distribution, and if we don't divide the incoming wave strength by the sum of them, we don't find a difficulty. But this is not an artificial selection. This kind of local homeostasis occurs in real brain by inhibitory interactions. After finding the critical point, we measure the first return time of these growth processes. In particular, we measure the characteristic times Tx for each individual run for 10,000 random independent realizations with different omega i's. We did a histogramming of these Tx values at the critical point and also below, and we found this probability density function graph, which shows for different coupling strengths power law tails, continuously varying power law tails. At the critical point, we can read off by fitting the critical exponent 1.2, but even below the transition point, we can find these power laws with k-dependent exponents, which agree well with the experiments of activity durations for real humans. These results were published in scientific reports in 2019. The next thing we investigated in collaboration with Gustavo Deco was to show what happens if the omega I distributions are very narrow and have a small mean value, because brain experiments shows that these omegas cannot be negative and they fall in a narrow band. Fortunately, there is a Galilean invariance of the Kuramoto equation, and non-zero omega I mean can be gauged out in a rotating coordinate system. And after a rescaling, existing results can be obtained at later times and at weaker coupling K. Furthermore, we investigated the effect of the addition of the annealed noise term to the Kuramoto equation. We did the same analysis as before, but we just found negligible effect of the weak noises for the duration power law distributions, as the graph shows. The conclusions: heterogeneity effects are simulated on large human connectomes. This enables us to distinguish from finite size rounding effects. Local homeostasis is needed to find criticality. We established a new method to determine crossover to desynchronization and to measure the characteristic times. The most important thing is that below the transition point, non-universal dynamical scaling of synchronization was found, which can be explained with the so-called frustrated synchronization in modules. The desynchronization duration exponents tau agree with the in vivo activity experiments for humans. These results are valid for realistic narrowband omega I frequency distributions, and they are insensitive for weak additional Gaussian noise. Further details will be published in Journal of Neurocomputing, and the preprint is already available by the archive website. Thank you for your attention.
Okay, thank you very much, Geza, for your interesting talk. It looks especially useful, let's say, for computation neuroscience, I mean, people are never sure if they are seeing synchronization or not, depending on the noise, the level of noise, or if the synchronization is too weak or not. Well, I'm leaving perhaps to the audience if they have any question. But meanwhile, I can go a little bit farther with that. So if I'm not wrong, you had an order parameter that was pretty small, right? It was 0.08 at some point.
The synchronization, the Kuramoto order parameter?
Yes.
Yes, it was rather small indeed. It corresponds to some partial synchronization because, yes.
But are we sure, let's say, that we are talking about partial synchronization and not, let's say,
no, in finite dimensions, you can never find the full synchronization. It can only happen in a very high infinite dimensional limit. So there is always crossover that you can find in lower dimensions. And the effective graph dimensionality is about 3, slightly higher than 3, thanks to the long-range connections. So you have the embedding space, which is 3-dimensional, and you have extra this long range, and this provides you a graph dimension, which is slightly higher than 3. But here you don't really have a real phase transition in the sense of synchronization.
Okay. And another question can be related to the fact that you are looking at a human connectome that is already a functional network, right? So
it's a structural network.
It's a structured network, this one?
Yes, yes.
Okay.
The connectome was structural one, yeah.
Okay, okay, perfect. Okay. So if we have any question, I don't think we have one from the audience. Okay, so let's thank again the speaker. It was a very nice talk, and let's move on at the next speaker. The next speaker will be Oscar Fajardo Fontiveros from Spain, Rovira y Virgili, if I'm not wrong, and you are a PhD student there, if I'm not wrong, right?
Hello, can you hear me?
Yes.
Okay, I'm going to share my screen to share a video.
Yes. So Oscar will talk about metadata analysis in order to predict links in a bipartite complex network. So please go ahead.
Can you see this?
Yes. Be careful maybe to share also the voice because we are still suffering from this. Okay.
That's good. Let me... Hello, my name is Oscar Fajardo Fontiveros, and today I'm going to explain my work that is called Using Metadata for Link Prediction in Bipartite Complex Networks. So let's start explaining the recommender system problem. This problem consists in, from known preferences, I have to predict new ones. And as you can see in this picture from here, we can map this problem into a link prediction problem, where the links are the ratings that the user puts to the movies and are labeled according to the root ratings that they put. Besides all this information, we have also more information about the nodes, like the genre, the gender, the age, and so on. So, for example, if I have a set of children who loves animation movies, maybe using this information, it can improve our performance of the when we want to make predictions. But maybe we have also random people with random ages who also love this kind of movies, and then this kind of metadata, that is, these node attributes, cannot be useful to make better predictions. For that reason, I want to answer these 3 questions about this metadata. Which metadata is important to make predictions? How can metadata help us? And when can metadata help us? I have to add to all this that this work can be applied to any kind of networks that you use. For example, bipartite like this, or a monolayer, a multilayer, and so on. So let's start explaining how I'm going to add my metadata to my bipartite network, and we'll be doing this. We are going to create this structure where we put our server ratings and our other bipartite networks of metadata, and we put everything together, creating this multipartite network. So when I want to make predictions, I have to take into account this structure, but also this metadata structure. Okay. To find the model who will predict my links, will be defined by this parameter p. I have to maximize this probability from here. That this is the probability that my parameters that defines this model that I'm looking for is the correct one given my observer ratings and my observed metadata. To compute this probability, I will apply the Bayes theorem, and after that, I will apply logarithms in both sides, and I will get this expression that in theory there is a constant here, but I'm not going to put it because it doesn't depend on the parameters, so it's not relevant to maximize this probability from here. The first term that appears is the log likelihood of this probability. Okay, that tells me how likely is my observed ratings given my model, my model. And the second one is the same one as before, but as you can see here, we change the observer ratings by the metadata. And also we add this hyperparameter lambda that tells us how important will be my metadata when I want to make predictions. For example, if I put lambda equal to 0, in this case I put every lambda with the same value lambda, okay, every lambda sub I is equal to lambda to illustrate this case. If I put lambda equal to 0, it means that I'm going to have only this expression. Okay, so this probability will be equal to this one, meaning that I'm going to take only into account my observer ratings. But when I increase a little bit lambda, I will start to observe the metadata and to take into account this metadata. For lambda equal to 1, all the metadata will have the same weight as the observer rating, so I will take into account everything with the same weight. And at the end, when I have large lambdas, my metadata is so important that I'm going to start to ignore this, the observer ratings. So the model that I'm going to use is called Mixed Membership Stochastic Bloom model. And the first thing that this model does is to suppose that every node belongs to different groups. So with different probabilities. So this user from here has a high probability to belong to this group, and less probability to belong to this group, and less probability with the group number 2, but cannot belong to group number 1 and 5. And also, the second hypothesis that it does, this model, is to suppose that the probability that two nodes are connected depends only on the groups that they belong. So, nodes from group 1 and 2 will be connected to users of group 4, 1, and 2, but with a high probability to be connected with users of group 4, but they cannot be connected to users of group 3 and 5. I have to add that the memberships that I'm looking for, these probabilities from here, they have to take into account not only the observer ratings, they have to take into account the whole structure of the multipartite network. So let's explain now the experiments that we are going to do. First of all, we are going to generate synthetic networks using predefined membership vectors with different profiles of membership vectors. Okay, for users I use 2 different profiles of the membership vectors, and for movies I use 4 types of the membership vectors. Why I'm doing this? Because I want to create full correlated membership vectors and metadata. So to each profile of membership vector, I put a different label of metadata. In this case, I have 2. So with that, I have 100% correlated membership vectors with metadata, and now I want to remove some correlations. How am I going to do it? Imagine that I want a 75% correlated membership vector with my metadata. So what I'm going to do is to iterate over each label, and with a 25% of probability, I'm going to change the label to a random one, to another random one. So here I'm going to show you the performance of the 100% correlated metadata with my membership vectors. Respect not having metadata, that is represented by this blue line. This red lines represents the maximum relative performance that I will get if I take the generative model and I compute the performance. So for lambda users equal to 0, we get this evolution of the performance, and we can distinguish between 3 different zones. The first one is when I cannot see everything, anything about metadata. As you can see here, I have the lowest performance. Here, on the other side, I have the highest performance when I basically see only the metadata of movies. And here in the middle, I have an abrupt change between this zone and this other zone. Then let's increase a little bit lambda users, and because I'm increasing lambda users, I get more performance, but the same behavior as before with the 3 different zones. And if I increase more and more until I reach this limit that I put here, we achieve the maximum performance that I can get. And if we check the evolution along lambda users, we observe the same behavior as the evolution with lambda movies. So now let's remove all the correlation. If we remove all the correlation, we can observe the 3 different zones, exactly the same one as before, but in this case, as we increase lambdas, the performance is worse than not having anything of metadata. So in this case, the best option that you can choose is to not put metadata if you don't have correlation. And now let's observe what happens if I have a partial correlation. In this case, 50% of correlation. Here I can observe the same 3 regimes, the same 3 zones, but in this case I have a maximum when lambda is equal to 1. So here the best thing that I can do is to observe every part of my multi-party network with the same weight to get the maximum performance that I can get. And now let's put here a real case, okay, that I get it from this dataset that is called MovieLens dataset, where I have users who rates movies, okay, and I also have the metadata, real metadata with real users and so on. For users, I have the gender, and for the movies, I have the genre. And in this case, we can observe that we have a maximum here for lambda equal to 1 in both metadata, users and movies. So that's it. The conclusions that we have here is that we find an inference approach for multi-party networks that can help us to put metadata and make link prediction tasks, okay? Also, the importance of metadata in the inference process results in abrupt transition in this link prediction performance, And the last conclusion is that the correlation of metadata with the connectivity patterns of individual nodes, we observe different behaviors of the performance in the link prediction task. Thank you so much. Any question?
Thank you, Oscar. Thank you. Thank you very much. It was very nice. So multipartite networks. Okay, fine. I have a question myself, but we have a question from Jean-Francois. He's asking about the objective parameters, how many they are, and do you have freedom in choosing them?
The parameters, the only freedom that I have, let me put this.
Because it looks like you have only lambda, right? Like your control parameter here.
Yes, the only control parameter I have is lambda. It's basically an hyperparameter that I put a posteriori to observe, to say if I want to see more about my metadata and my observed ratings. But also I have to, according to that lambda, I have to look to the best partition, the best probability groups to fit my metadata and also my observed ratings.
Okay.
For each metadata, I have a different lambda.
Okay, and Joy O'Brien, he's asking about, do we have any prior information in the Bayesian framework?
The prior is the metadata, because here we don't put it very clear. Well, the prior in fact is the metadata itself. Because when we did the original formulation, this is, let's say, an illustrative formulation of our posterior, because this is a posterior, that's for the patient people.
Yes.
We put here this as a prior, and then this is the likelihood, and this is the prior, and our prior is the parameters who fits also the metadata. So the metadata is our prior.
Okay. Because a question that it looks, I mean, initially at least weird to me. So why we should increase lambda up to 1000? It looks like your side data, and then can be gender and so on, are much stronger than your prior data that you have the interaction between movies.
Yes, at the end with lambda equal to 10, in a lot of cases, it's enough to forget about your observed ratings.
Okay, but it is not distorting, let's say, the prediction at the end. So because I think that the main, let's say, network, let's say it in really poor words, it looks to be the relation between individuals that we have and the movies, right? The other data, are they side, let's say, a second order data in this sense, or not? Because if you put a lambda quite large, they are not anymore a second order data, right?
No, I don't think so.
No. I mean, I was just curious. So I had the feeling that it was somehow distorting the prediction.
No, but
they are quite large.
As I say, it always depends on the correlation at the end.
Yeah.
How metadata depends on the structure of the network.
Okay. Thank you again. Thank you very much.
You're welcome.
So let's move on with our next speaker. Our next speaker is from Moscow University, Mikhail Tam.
Yes, hello.
And he's working on, or at least this work is in hyperbolic graphs. So models about the hyperbolic graphs. So please go on with your presentation. The floor is yours. You can share.
Yes, I have a very
yes. Okay. Okay.
It works. I have a pre-recorded presentation, and hopefully it will work now.
Just share your voice, because sometimes with the computer.
Let's see if tell me if it doesn't.
Yes.
Hello, my presentation today is dealing with the properties of hyperbolic geometrical graphs, and I will start with reminding you of the properties of these beautiful objects. It has been known for the last 10 years that if you construct a graph according to the following procedure, you take a disk of a given radius on a hyperbolic plane, then you distribute points at random on this disk with some fixed density, and then you connect all points which are distance less than r from each other on this disk. Then you get a graph which has several beautiful properties. Most importantly, it is a scale-free graph with a degree distribution with a power law exponent -3. It is small world in the sense that it has a very small diameter, and it has a large clustering coefficient which remains finite in a thermodynamic limit in a limit of large R. All these properties are common in experimentally observed networks, which makes the hyperbolic random graphs a good candidate as a proxy to study real-life networks. And this idea have gotten some traction, but in my opinion, there are certain, well, from my experience, there are certain difficulties in distributing this idea to the general community. One of them is that many people are not very familiar with the notion of hyperbolic plane, and even those who get interested, they often get somewhat rebuffed by the technical difficulties of the consideration. Indeed, if you look at the original paper, then the degree distribution, the average degree of a node as a function of its position in space is described, for example, by the formula which is written over here, which, after taking some proper limits, gets you to some beautiful limiting results. But it is very difficult to see this hidden simplicity in these cumbersome formulas. So that is my main question, which I was trying to address. Is it possible to find a more intuitive, more easy to explain and more easy to understand representation of these results obtained by these results for the hyperbolic random graphs? And the main idea of what I'm going to speak about is based on following. Basically, the very first thing you learn when you start discussing hyperbolic plane is that the size of hyperbolic disk grows exponentially with its radius, and as a result, it is possible to uniformly embed a tree into a hyperbolic plane. In a sense, a tree is a natural discretization of a hyperbolic plane, as shown, for example, here in a Poincaré representation. And therefore, it makes sense to ask yourself, if an infinite tree is a natural discretization of a plane as a whole, is it possible to think of a finite tree as a sort of proxy for hyperbolic disk? And that is what we're going to try to do. We take a finite regular tree, like shown here with 4 generations and with degree 3, and then you need to define some sort of distance on this tree, and it is there is natural definition of distance, which is the number of links connecting 2 points. And in a sense, if you go back, this distance is actually a reasonable proxy to the true hyperbolic distance if you embed this tree uniformly in a hyperbolic plane. And then your analog of the Krukov and Dole procedure will be defined as take this tree and connect all the points which are separated along the tree by no more than n links. For example, in the simplest possible case, when you have a tree of 2 generations, you will get a graph like this. If you take a tree of 3 generations, it is already quite difficult to follow the details of such a tree. But nevertheless, you have this general property that the center of the tree is connected to everybody, and the nodes of this first generation are connected with smaller number of nodes, and so on and so on. If you look if you try to quantify it, you will see that, for example, for a tree with 4 generations, the central vertex has degree 45. Then this vertex of the first generation have degree 29. This one has degree 21, and so on, 13 and 9. And you can ask what is the general formula for the degree distribution as a function of or degree as a function of the generation. One possible way is to write down a recurrence formula, which is relatively easy, but there exists even simpler way. If you look at this, for example, at this picture, you may notice that all these green points here are defined as points at distance not more than 4 from the red point. But you may notice that they are all of them are simultaneously at a distance not more than 3 from this point surrounded by a circle. And this is a perfectly regular tree of 3 generations, and you can write down its size, and therefore and this idea which is replacing the red point as a center by a point which is halfway from the red point to the center of the whole tree, it holds for any p and any number of generations, and it allows you to write down the explicit formula for the degree for degree as a function of generation. And then since you know the number of nodes in each generation, you can just simply write a degree distribution, which is essentially log periodic distribution with a slope -2 and with log periodic support and slope -2. However, which is to be expected because since it has log periodic point support, the slope should be different from the continuous variation by adding 1. So there was -3 in the Krukov representation, and it is -2 here. However, you can see that the average degree diverges proportionally to the square root of the total number of vertices in this system. Square root of the total number of vertices of the system, which is not particularly good, but you can think of various ways of rectifying this problem. One is to, mostly following the idea of the original paper, to introduce density of nodes, that each node is occupied with some probability which is going down with growing n, and then you can, if it goes down like this, you can make the average degree finite in the n to infinity limit. Another way is to decouple the radius of the connection radius from the number of generations, and then the average degree will be L-dependent constant in the end. If you go along the first way, you get the degree distributions which are basically like these, which are shown for average degree 1 and average degree 10. And you see that they are for the small degrees, they are essentially a power law with slope -3, and then they become more and more modulated because the central limit theorem dictates that the width of distribution around the original points of support is getting less and less wide. Secondly, if you decouple the size of the tree from the connection length, you get a curtailed. Essentially, what you get is a network with a core shell structure. In the core, far away from the boundary, all the nodes have the same degree, and in the periphery, you get a curtailed scale-free degree distribution. However, the size of the core is essentially exponentially small in the connection length, and therefore it results just in a single point like this in the degree distribution. So essentially, it is a curtailed power law. Summing up, you see that these discrete hyperbolic graphs, they have scale-free, or depending on the variety, you can call it semi-scale-free degree distributions with exponent -3 in discrete case and -2 in discrete case and -3 in continuous case. It is easy to see that diameter is either finite or at most logarithmic at n. The clustering coefficient of the points in the periphery is exactly 1, and therefore, because they remain a finite fraction of the system, the total clustering coefficient remains finite in the n to infinity limit. All these properties are essentially reproducing what we know from the original papers on the discrete geometry, on the geometric random graphs on hyperbolic plane, but we have re-derived it for an object which is much more simpler, much more easy to explain, and therefore, in my opinion, it is both pedagogically useful and may give you a better insight on how these properties emerge and why they actually emerge. Thank you.
Thank you very much. Thank you. It was a very nice talk. Let's wait for any question from the audience. Meanwhile, I was wondering, so even for myself, the hyperbolic geometry of networks has been always a nightmare. So I never even tried to finish reading a paper. But this way, it looks to me like discretizing the hyperbolic graphs like you propose. Maybe I'm wrong, but at least the graph that you reconstructed at some point, it looked to me like the original hierarchical graphs. I remember a model by Barabashi that it was quite similar to the one that you. Is true that this way you are mapping the discretization, at least, of hyperbolic graphs to.
I think there must be some sort of connection. I should look into it. It is an interesting question. I think that it should be similar. Yes. Okay. Anyway, well, yes. Well, my motivation of all this story was that, well, I spent quite a lot of time trying to understand it, and then I understood that I'm completely unable to explain it to people, and after some, and here, well, the somewhat annoying thing is that when you start introducing some randomness, you get this mixture of discrete and continuous power law, but maybe it is possible to circumvent it somehow by introducing some sort of multiplicational randomness rather than additive randomness, in a sense, like by varying the degree of nodes, and because that will give you a multiplicative randomness in a sense.
Okay, okay. Thank you very much. Let's see if we have any question. So no questions. So thank you again.
Mm-hmm.
And we are moving now at our last talk for today. Arkadiusz Jędrzejewski. Oh my God.
Jędrzejewski, yes.
Okay.
That's correct.
From the University Wrocław, University of Science and Technology, from Poland.
In Poland.
Will be about Q-Voter model analysis using quenched and annealed randomness.
Yes,
so
that's right.
Please, the floor is yours.
Okay, so I'm starting to sharing the screen. Yes. And now is it?
Yeah, it's fine. It's perfect.
Okay, so welcome everybody. I'm Arkadiusz Jędrzejewski, and today I'm going to talk about the nonlinear Q-Voter model, and we are going to analyze different phase transitions this model exhibits, and we will add to our system different kinds of randomness. So let me start with an explanation what kind of randomness we are going to cover. So in statistical physics, there are basically two kinds of randomness. The first kind, the annealed randomness, corresponds to some properties of the system that vary randomly in time. In contrast, quenched randomness corresponds to such a situation in which these properties are frozen in time. However, they are randomly distributed at the beginning of the system evolution. And it turns out that these two types of randomness are relevant not only for physical systems, but also for social systems, and are important for modeling human behavior. So, for example, in social psychology, there is a very well-known long-standing person-situation debate, and this debate boils down to the question whether personality or situational factors are better predictors of human behaviors. And when we think about this question, then we can argue that the human behavior that results from personality can be viewed through prism of quenched randomness, since personality is postulated to be stable and enduring over time. So our behavior should also have these properties. On the other hand, when we think about human behavior as a result of situational factors that can change from one situation to another, then our behavior can also change, and this resembles more annealed disorder. So this person-situation debate as an inspiration for our study to introduce these two types of randomness into one of the models of opinion dynamics. So let me define this model. So we choose a nonlinear voter model to study this, this system. And in this nonlinear voter model, it's an agent-based model. So that means that we have a network of agents. In each node in that network corresponds to one agent. And of course, agent may interact through links in that network. And in our study, we choose a complete graph topology. And this is mainly because on this structure, we can obtain strict mathematical formulas, so we don't have to rely only on Monte Carlo simulations. And Q-Voter model is also a binary state model. That means that each agent has a binary opinion on a specific subject. This opinion is represented by a variable that can be into states, and we will refer to these states as positive and negative opinions. So let me now present the dynamics exactly. So let's imagine that this is the part of the network. And first we choose randomly one voter. And then from direct neighborhood of this, this voter defined by the network topology, we choose Q its neighbors. And these neighbors form a group of influence that tries to force some social pressure on this initially chosen voter. And when this group is unanimous, so all the voters in the group has the same opinion, then our initially chosen voter changes its opinion to the opinion the group has, like in this example. And when this group is not unanimous, is divided in opinions, then our initially chosen voter also can change its opinion, but this happens only with some probability epsilon. So this model has two parameters, the influence group size, which is obviously an integer, and also an epsilon. So this is this corresponds to some level of noise in the system, and this refers to this probability of opinion change under the case that the group of influence is divided in opinion. However, there is also another formulation of this model. And in this equivalent formulation, it's enough to give the flipping probability. So this is a probability that a given voter changes its opinion to the opposite, given that we know the fraction of disagreeing neighbors with him. And in this formulation, we see that Q don't have to be just an integer, since this formula gives correct values also for any real positive values of Q. So in such a sense, we can extend the domain of this parameter. And now we only have to answer the question how we can introduce these different type of randomness into our model. And we do that in regard with this parameter epsilon. So in our model, each agent has its own parameter epsilon. And now depending on the distribution of this parameter in the system, we can talk about situation or person approaches. So in the situation approach, all voters have the same value of epsilon. So epsilon corresponds to this probability of changing a voter's opinion in the case of disagreement in the influence group. However, in this person approach, and this situation approach corresponds to the original formulation of the model. In the person approach, on the other hand, we divide our community into two separate groups. One group consists agents that always change their opinions in the case of disagreement in this influence group, whereas the rest of the voters never do that. And they form this second group. And in this approach, this epsilon is now the fraction of voters that always change their opinions. So they have this value of epsilon equal to 1. And now in such systems, we ask the question, will we observe any differences between such formulated models? So, but before we answer this question, we have to define what we are going to measure exactly. So in order to define different phase transitions, we have to define an ordered parameter. And in our case, this is public opinion, which can be rescaled to the concentration of positive voters. And in fact, we will use this
I guess we lost you. It looks like we lost you. I don't know why. Can the other hear me or?
Yes, we can hear you.
Yeah, so I think that we had some problem with Arkadiusz. We lost him at some point. Oof. Okay, I don't have his presentation, so I cannot do it for him. Let's maybe wait a little bit. I think his internet turned off. I mean, it happens to me sometimes. But it started to be nice, honestly, but I mean, it happens always like this when you start with your mean field formulation, everything breaks down. Okay, I think we lost him. I don't have his contact, so. Okay. Anyway, so I guess we have to close here our session. We lost one of the speakers. He realized because he's disconnected. Yeah, well, is someone in contact with him maybe? I mean, a friend or a colleague, or otherwise I have to close it because we are almost in the limit, so. No. Okay, it's a pity. Anyway, I think that there is a possibility to record the talk and to ask the organizers to put it online like all the others. So, okay. So, thank you for everyone, to everyone for participating today. There were some very nice talks. Unfortunately, we lost the last speaker. So tomorrow will be the last day of the conference. I invite you to follow as much as you can, and see you tomorrow then. Okay, so bye to everyone.
Bye.